The consequence is that in warm El Nino years, we don't have that influx of cold water that's also bringing with it nutrients to replenish what phytoplankton used up in the surface waters. And without that nutrient replenishment, we don't get algal phytoplankton growth, we don't get zooplankton, we don't get fish. And so in El Nino years, we see a breakdown of the fishing industry, and we also start to see that the organisms that eat fish here also start to have population crashes. And in extended El Nino periods where it goes on for several years, that can really affect biodiversity along the coast of South America, in addition to fishing, which is kind of like why we notice it here. Okay. The breakdown of that wind pattern affects not only this region in this specific way, but it means that wind patterns globally are disrupted. So we get droughts in some places where it normally rains, we get heavier rainfall in other locations where the precipitation should be moved out. And that disruption of movement of moisture and temperature then can imbalance other ecosystems. What's interesting about the El Nino La Nina cycles are that it's normal. This is supposed to happen, okay? Like this happens on a scale that we can kind of predict almost, like every 8 to 10 years we should see this. But they seem more intense and they seem to last longer than they have in the past. And that might be a sign that the system is fundamentally changing. If now the norm is El Nino, and the in-between times are upwelling. What does that mean for the ecosystem? And that's the question. Okay, so everybody.
Wait.
Yeah.
Are we always like in an El Nino or La Nina, or is there like periods of times?
No, there should be periods of times. I would say that in looking at this data, it's either El Nino or La Nina, right? And that's because we're looking at kind of these big changes. I would say like the data set is graphed in such a way so that you can see this upward downward trend. But I would say the intense, what we would like see as a headline or the NOAA would report as an El Nino or La Nina is probably only when it gets above like 1.5. Okay, there's a normal variability with seasonal cycles. And what we think of as like, oh my gosh, this is a really an El Nino is when it gets really extreme on another one of these ends. Good question. Cool. Did I mention how do we get this data? How do we know what sea surface temperature is? I think I did. You can have people out there with thermometers. That works. A lot of what we do today in terms of sea surface temperature comes from drifting buoys that we have put out largely for weather forecasting purposes that are measuring sea surface temperature. And they're in these big currents, and so at any given time, then they're sending their data to the satellite of what temperature, what salinity is like, what the waves are like at that location. We've also done a lot where we put sensors on ships that are going across the ocean. And again, real-time reporting of what sea surface conditions are at that location. Gets radio up to the satellite and back down to the scientist. That's important for shipping so that we can avoid storms. But it turned out to be this huge data set then that oceanographers can work with about basic conditions. That's just kind of passively taken. The ship data is pretty confined to major shipping lanes. So we only can look at reliably a certain portion of the ocean. The other, kind of data comes from satellites that we have tuned to looking at sea surface temperature, sea color, sea height. And those, again, all of that data goes into these big giant data sets then that you get to number crunch and computer program in order to pull out graphs like this. Cool. All right. So we ended class, we did this M&M experiment. And we looked to see what colors of M&Ms, come on in, had disappeared at different times. And there were kind of two questions to understanding light variability in the oceans. And the first one is, what is the fate of visible light in the ocean? Like as you go deeper in the ocean, what just happens to bulk light in general? It plummets. It plummets, right? You lose quantity of light as you go deeper in the ocean. And this sets up fundamentally different ecosystems, different biomes in any given water column. You got the sunlit surface waters, you got this kind of twilight zone where the light is petering out, and then you get down into the midnight dark portion of the water column. It gets deep enough where there isn't any visible light available to organisms. And again, then you're going to start to have adaptations of organisms to the quantity of light, right? Like down here, you have organisms that make their own light for different purposes, mating, communication, finding food. And then some of the surface waters, you have photoautotrophs, algae, all kinds of seaweeds and kelps doing photosynthesis. In the deep ocean, you have chemoautotrophs doing chemosynthesis in the absence of light. And that fundamentally sets up the food webs and trophic pyramids in different ways. The other thing we saw with our M&Ms was the next question is that what happens to the quality of light as you get deeper in the ocean? So the quantity declines. What happens to the quality of light? Which M&Ms disappear first?
The dark ones.
The red ones.
The brown and the brown ones.
And the brown and the orange one, right?
Yep.
So we had these little M&Ms out with the plastic on top that was blue. And if you put enough plastic on it, the different colored M&Ms disappear. And it simulates going deeper into a water column. And that we see that the different wavelengths of light penetrate to different depths in a water column. And that has implications for not only quantity of light, but then the types of wavelengths of light that are available to organisms to use for vision, for photosynthesis. Okay, so the quality of light changes too. And in general, the reds, the orange, the purple colors are lost first. They're both absorbed by water molecules and they get reflected away and go in different directions. And the blue wavelengths tend to penetrate the furthest. And that means that when you're looking at a big body of water, there's mostly blue light that's available to be reflected back to your eyes. And that's why we observe the big body of water as blue, because that's the wavelength that's lasting the longest for then us to observe as a color. So the quality and the quantity of light change as we move downward and get deeper into a body of water. The general term for this is light attenuation. And usually, again, we think of light attenuation as a decline in the amount of light, and that definitely happens. For every 75 meters that you go down in the world's oceans, there's a 10-fold reduction in light. So at 75 meters down, there's 10% of the light at the surface. Once you get down to 150 meters, there's usually only 1% of the visible light total that's available for organisms. Okay. This has big consequences when you add in wind and wave currents. And if you have organisms that are up at the surface and they're getting mixed down deeper by wave action, they're going to be up where they can photosynthesize, and then all of a sudden they're going to be where they're not. And then they've got to rely to come back up. And if you get big mixing events, you can mix those organisms far enough down that they don't photosynthesize enough to have net photosynthesis, to have net carbon production. And so this idea of kind of where you are in the water column in terms of depth is really important for organisms. And then first and foremost, it's important for light availability. Okay, so again, as you're going down in the water column, you lose the amount of light, and you lose the types of light wavelengths that are available for you. And so it affects primary productivity. We see in the world's oceans then that sea surface phytoplankton are really tuned to pick up in the blue spectrum, and they tend to reflect in the other ones and be kind of a greenish color as a result. As you get nearer into shore and you have more the sediment in the water column, the organisms might be more attuned to picking up a red, orange, violet wavelength in order to use for photosynthesis, rather than the other ones, because that's what's available to them, and that's what's going to be most useful then. They're adapted for that type of condition. We see too it affects body color. If you want to blend in, you got to be the color that's there to be utilized in the water column. So as you get into open ocean ecosystems, you see lots of blue, lots of gray colored organisms. As you get down into the deep ocean, we see lots of red and black and orange organisms because they blend in with the blackness of the water that's there. The red doesn't stand out like it would in a coral reef where there's red wavelengths of light to be observed. Kind of cool. You also see eyes that are very affected by the quality and the quantity of light. At the surface, you have fish have eyes like us, kind of normal body size. As you get deeper in the water column, you get bigger and bigger eyes physically. In general, there's less light to be had, and you need a bigger organ to get the same amount of information. You get eyes as you go down in the water column that are oriented upward on the body of an organism, because that's where the light is coming from, is above them. And if their eyes are just on the side of their head, the bottom half of their eye doesn't see anything. There's not any light there. Okay. And so there are these interesting adaptations, this fit between form and function, where light is acting as a natural selective agent, as we're going to talk about it next week, in terms of evolution, as an evolutionary pressure on aquatic organisms. That's totally different than here at the surface, where we're like bathed in and surrounded by light all the time. And the thickness of the atmosphere doesn't determine what types of wavelengths of light and how much light we get. Okay. It's totally different in aquatic ecosystems, where the water molecules themselves affect the quality and quantity of light. Are you with me? Okay, I'm not talking crazy talk yet. Some of those interesting things. All right. The other big effector in aquatic ecosystems is temperature. And there are a seasonal pattern to temperature, which we're going to talk about. But we also see there is a very defined depth pattern to temperature as well. Okay. And in general, the shallower you are, the closer to the surface, what is your temperature?
Warmer.
It's warmer. Why is it warmer?
The sun.
The sun. You're closer to the sun. It's warmer. Okay. That's totally it. The surface water tends to be warmer because it's receiving more solar radiation. Okay. What happens to temperature as you get deeper?
It's colder
It gets colder. Why?
because it's not getting the solar radiation.
It's not getting the solar radiation. Okay. As you get deeper, you don't have the light, you don't have the warming, it's colder. We tend to draw our graphs of conditions and concentrations of organisms and abiotic conditions in this kind of inverted graph form when we're talking about aquatic ecosystems. We put the x-axis at the top, and then we draw increasing depth usually on the y-axis going down. Okay, and so you can think of this as like 100 meters under the surface. Okay, we're going from 0 to 100 instead of 0 to 100. It's because we're always thinking of this downward aspect to the water around us. And it ends up making the graphs look a little funky, and it's annoying to make your computer draw them right. If you have to graph aquatic things in the way that oceanographers report stuff. But just keep that in mind. We're going to look at several what we call these depth profile graphs here. And they are graphed in a unique way compared to how we tend to think about the x and the y axis. Okay. We think of this top upper surface water as being what we consider the epilimnion, the sunlit surface water. Down below, you get into the hypolimnion. This region, where the temperature changes really dramatically from the warm surface water to the cold water down deeper, is what we call the thermocline. Okay? A thermocline is an area of rapid change in water temperature. Yeah, so you have a question? You look like you're like thinking.
So like the thermocline, does it have like, so it has temperature between like the upper level, which is
Yep.
hypolimnion, and
The hypolimnion, which is below. And again, on this particular one, we're drawing a very idealized water column where it's really warm at the surface and it's 4 degrees cold at the bottom.
so is there like fish or like other species that are adapted to that level?
Yes, exactly. Because the temperature is warmer at the surface, organisms that live up there are going to be optimized for warmer temperatures than the organisms that live down deep. Okay. And the ones that live down here, it's going to be cold, and it's going to be cold all the time, no matter what the season is at the top. Okay, and so they're very adapted for this stable, cold, salty, dark environment of the ocean versus the variable, warm, sometimes it's fresh water, sometimes it's salt water, sometimes it's cold time surface water that you can get. And the steepness of that thermocline, what the slope of that line is between upper and lower bodies of water, and the depth at which it covers can vary a lot. Okay, we're going to start with this one as our like perfect world ocean in summer. And then I'm going to say, what happens when it's winter? And that's the next slide. Okay. All right. Notice that the profile for temperature is a mirror image when we want to look at density. Okay. So this warm sunlit surface water is less dense water than the colder 4-degree water at the bottom, which is higher density. Remember, one of the properties of water is that it's most dense at 4 degrees Celsius. That's what gets this 4-degree water down here deep, because it's the most dense. As this 4-degree water gets colder, it starts to freeze and the ice pops to the surface. Okay. Cool. All right. This density gradient, caused usually by temperature, sometimes by salinity, means that the surface water is separated or stratified from the bottom water, and that it takes a lot to mix the two. Okay. And it's almost like what he was getting at, what's in the surface is this whole other world than what's happening at the bottom. And nutrients, organic matter, oxygen cycle very differently in the two parts of the water column. Yeah.
So like the thermocline,
Yeah.
since it's a zone of rapid temperature change, doesn't like the fishes that live in that zone are adapted to like both temperatures?
Yes, they are.
So they can go like deeper and then
They can come to the surface. And it turns out the largest migration on Earth is actually the daily migration of deep water zooplankton and small fish that hide down here in the dark of the ocean during the day. And then they travel upward through the thermocline to get to the surface waters to eat algae at night, where they're relatively safe from predators. And then at daytime, they seek back down to depth. And so they have to be adapted to this huge range of conditions. You'll have these little shrimp that swim like 2 kilometers a day to go from hiding to like eating and then back. That's also where a ton of oceanographic research happens at night, because that's when it's easy to get to those organisms when they come up to the surface anyways. Good questions. Okay. Temperature, linked again to solar radiation variances, it sets up this stratification in the water column between warm, low density water at the top, cold, high density water at the bottom. And again, this is what we would consider in this instance of, 18 degrees Celsius down to 4 degrees Celsius at the bottom. That's summertime, world oceans, deep water lakes. Okay. All right. Temperature, though, we know, varies seasonally, and that affects water temperatures too on a seasonal basis. Okay. And so the temperature profile, how it varies from top to bottom, how it varies with depth, and the steepness of that thermocline all vary with season. They all vary with mixing. If you get a huge Hurricane Dorian that comes through, it'll disrupt that water stratification. The wind and the waves will mix all of the water together, top to bottom. And it varies with latitude, okay? As you are in the tropics, stratified, warm at the top all year round. At the poles, though, it's a very different scenario because you start at a different place in terms of surface temperature. Okay, and we'll walk through these as I talk about this particular graph. Okay, but season, mixing, and latitude will all affect the temperature profile, the thermocline, the steepness of that thermocline in a particular water column. Okay, so the one that we just looked at, I mentioned, is the summertime stratified water column. That's this orange line, warm at the surface, big thermocline, cool at the bottom. That's also typical of tropical latitudes, equator to 30 degrees north and south. It's always hot at the top, it's always cold at the bottom, okay? Year round, because they just kind of have one solar radiation in it, okay? As you get into fall, let's go with that one here, is the red one. The surface water cools down. When the surface water cools down, it gains in density and it sinks. And when the surface water sinks, it pushes up some of the bottom water and it all mixes. And you get what's known as a well-mixed profile, where it's the same at the surface and at the bottom. There's very little or no visible thermocline big change, a big sweep. That's typical of fall, when we have what we call overturn of a water column. When that surface water gets cold and gets more dense, it sinks down and it mixes with the bottom water. It makes everything very similar top to bottom. It's also very, very typical of polar latitudes. It's cold at the top, it's cold at the bottom. Okay, that's just the way it goes. All right, the interesting stuff tends to happen in springtime and in the mid-latitudes. So in springtime, we have the start of the warming of the surface water. We get a less defined thermocline, but it's still cold down deep. Okay, that's very typical of what we find in mid-latitude bodies of water. It's not going to be as hot and as well stratified as in the tropics or in summertime, but you still start to get that separation of warm, less dense surface waters and more dense, cooler bottom waters. Okay. You guys with me? Yeah? Okay. I think that understanding temperature in water columns it's so key to what's happening on a seasonal cycle of primary productivity and with organisms and different environments. But it's also one of the most difficult things to understand until you're like out there on an oceanographic vessel and you're like watching the temperature data come up from the CTD dipper as it's going down. And you're like, oh my gosh, we just went through the thermocline. And you're like, it's real. Because we just don't experience this on a day-to-day basis. Okay, sometimes when you're in the lake in summer, the surface water is all nice and warm. And then when you get your toes down, it gets really cold, right? Your body is going and crossing the thermocline. Okay, it's going to be cold down at the bottom. If you dive down below that thermocline, you jump in. When you get up to the surface, you're in the sunlit surface waters. All right, interesting profile that's on here is wintertime. And this is an interesting one. It's cold and 4 degrees down at the depth. It's wintertime. Up at the surface, though, you'll notice that it's actually, we've got frozen water. Okay, coldest temperatures, ice environment in wintertime. And that's why it has this weird dip to the other side. Okay. It's less dense, but it's colder in winter at the top because you have ice. Okay. Cool. What's common for me to ask you, how am I going to like test you on this type of information? What was that?
So yeah, I was wondering about that.
Okay. Yeah. I'm not likely to ask you to draw for me this. Like that takes a lot of time on a test actually. I'm likely to give you this as a graph and say label summer, winter, fall, spring. Yeah. I'm likely to then ask a multiple choice question. Line A, is that typical of a tropical, a mid-latitude, a polar environment? Okay. And there's no line A on here, but I would put an A on here. It would be like whichever one it was, right? Okay.
Wait,
And it would be in color. And I would use this exact graph.
Yay.
So what does it mean when it says stratified tropical, stratified mid-latitude?
So stratified means that you have a thermocline and you have created a stratified layering system of warm water at the top and cold water at the bottom.
Oh, okay. Got you.
You can think of it, and you should, when we have this stratification, you really should think of it like a layer cake. And there's this thermocline of icing in between. They are two different things.
How come the bloom doesn't have a label? It's not like a reverse thermocline or something.
Yeah, it is, and we would still consider that like a thermocline because
Yeah.
it is. That's the definition of a thermocline, is that it's a rapid change in temperature with depth. It's just the opposite movement of temperature than what we would be more familiar with.
Gotcha.
You don't encounter that blue line unless you have ice. And so again, it's something that if you're in a polar environment, you're likely to encounter if you're going to a wintertime lake in mid to upper latitudes. You will never see that in the tropics because you never get ice formation. Cool. Okay. Question 3.6. Why does seasonal stratification of deep ponds and lakes occur? Why do you get the green and orange lines? What causes that?
Solar radiation.
Solar radiation. Okay. Yeah. I tell my biology students the answer is always water or hydrogen bonds if you're not sure. And in this class, it's the sun.
Blue sun.
If you're not sure, Okay, you guys feel good?
Feel great.
Yeah, actually that went well. It's like I can't remember how I learned this information, but I don't feel it went that easy. Information transfer. Okay, all right, cool. Okay, now we've talked about latitude change. We've talked about mixing. Mixing will always give you that well-mixed fall red line profile that we talked about. So mixing happens in fall because density changes and changes in solar radiation. Mixing happens when you have big storm events too. So hurricanes, even big storms on a lake will cause mixing, and you go swimming the next day and you won't have a thermocline. And it takes a couple of times to change. The other thing we see is that geography and topography can affect temperature profiles as well. And again, it's entirely linked to solar radiation and how much is available at any given spot. And so, of course, depth is going to influence that. If you have a deep pool and a river, it's going to be cold at the bottom, warm at the top. The steepness of the slope will also affect water movement. And the steeper the slope the water is running over, the faster the water moves, the less time it spends in any one spot, which means the less radiation it receives, the colder it will be. So in general, fast-moving water tends to be colder. Still water tends to stagnate and get really warm and sit there. Okay, so water velocity affects temperature. The other thing that affects it is, in this case, what this particular diagram is showing us is canopy cover. Okay, where you have steep, fast-flowing water, it's cold. When you get out here and it's going slowly, it tends to warm up. The thing that really affects it is when you don't have any trees to block the incoming sunlight, the water really heats up and gets much warmer. It's kind of cool. Right. And again, this is coming from a perspective that you go to a location and you measure water temperature and you're like, oh, why is it so much colder here than it is down here? Okay, and again, there can be a couple different factors that are playing into that, but it's all linked to how much solar radiation a spot gets. Fewer trees, more time in one spot, the warmer you're going to get, the more solar radiation you're going to have. The faster the water moves, the deeper it is, the more tree cover you have, the less solar radiation, the colder it will be. Again, this means that you'll find different organisms in this part of the stream than you will down here because the temperature is different. Okay, you'll find the cold water, fast-moving fish versus the still, warm water fish in these different locations in one stream. When we talk about mixing and overturn of water columns, this really affects nutrient concentrations. And that the nutrients in one part of the water column can be very separated from the nutrients in another. So if you have lots of still water that's warm, you have lots of light, you're going to have lots of photosynthesis. You're going to take up a ton of nitrogen and phosphorus from the water. Those dead plankton, when they die, some of them get eaten up there at the surface, but a bunch of them sink and die. Okay, and they get down deep in the water column and they're decomposed down deep. And so you have then a regeneration of nutrients down deep, but that cold water has to wait weeks till it's fall again to get mixed with the surface. So you can get nutrient limitation at the top where you have lots of photosynthesis in the warm surface waters. The nutrients are being regenerated by decomposition in a whole other spot in the water column. And that can really limit then phytoplankton growth and photosynthesis, and that then limits food webs, changes how they work in the short term. Okay, cool. All right, let's talk about salinity. So another thing that we mentioned that one of these unique properties of water was not only that it can absorb solar radiation, give it off, moderate temperature, but it's a universal solvent because it's that polar molecule and it has these partial charges on the oxygen and the hydrogen. And this means that it will dissolve the substrate that it's on. Like the ocean is constantly dissolving the ocean floor and the shoreline. A lake will constantly be dissolving the ions of the rock around it. And depending upon then what the substrate is that body of water is contained in, you'll get different ionic concentrations of different types of ions, and you can affect the salinity, which is how we measure solutes, I guess you could say, in the solvent of water. Seawater is a very particular solution that has a constant concentration of about 35 parts per thousand or 35 PSU salinity. And it varies just a little bit, but in general, you can go out almost anywhere in the world's oceans and you'll measure the salinity as somewhere between 34.5 and 35.5. Okay, that's salt water. That means that for every liter of the ocean, there's about 35 grams of salt stuff dissolved in it. Okay. So here's our 35 kind of parts per 1,000 seawater right in this range, what we consider saline water. It can be saltier than that. You get up into the 50 parts per 1,000, 50 PSU. PSU is practical salinity units. When you get into ponds where evaporation exceeds precipitation or runoff and input of water, and that leaves behind all the salts and solutes in the remaining water, and it can get really salty. You can go then from salt water to fresh water too. Okay, if you have lots of input of water, you'll dilute out those salts and you'll get your salinity really low, somewhere in the 0 to 5 range. You know, if you go and measure your top water with one of our pros later on in the semester, you should get a salinity of 0 parts per 1,000. Okay, that's what we consider fresh water. The range in between seawater and freshwater is what we call brackish water, when it's mixing between 35 and 0 parts per 1,000 PSU. Just like temperature has an optimum for an organism and a tolerance level, different organisms are adapted to different salinities. Lots of times organisms that live in the open ocean cannot exist in the brackish estuaries where the freshwater is coming in and mixing because the salinity is too low. Same thing, our freshwater fish and shrimp species, you can't dump them in seawater, they'll die. The really cool things are the ones that can live where it's super salty. They have really interesting regulation systems for maintaining ionic balance between them and their environment. Yeah.
Isn't there a like crater in one of these seas that like collects too much salt? And when like they're like crabs, like you can see like if they fall in there, they can't get out, and then they're just like and they like die. Like you see them like all around the edges of it.
Yeah. There are the new Blue Planet series, I think it's either the first or second episode, has this eel that goes into one of these brine pools. And there are certain places in the crust underneath the oceans, as well as some of our lakes, where you have really salty water that's coming up, like it's dissolving more substrate in that region than normal. And you get this really briny, salty water there. And the organisms, for normal saltwater conditions, when they get in it, they like die if they're in it too long. So there's this little eel that's like swimming across it, and it like dips in and it comes back out, and then it dips in and it's like there for a while, and it comes out and it's like having a seizure because it's like going into shock from too much salt, essentially, both like rushing in and losing too much water to the outside environment to maintain its osmotic balance. Yeah, it's pretty cool. Doesn't happen all the time, but it does. The other thing I want you to think about is that salinity affects density too, right? The amount of stuff in the water will make it more or less dense. So fresh water has a lower density than salt water because it doesn't have a bunch of stuff dissolved in it. And so fresh water will float on top of salt water. At our deepest, darkest oceans have a slightly higher salinity rate than the surface water because there's not an input of precipitation to them to dilute them out just a little bit. And that slight difference in salinity top to bottom in the world's oceans, at the top where you've got a little bit of evaporation but you have more precipitation versus the deep, dark, salty ocean, helps maintain that stratification that's set up by temperature. And we often observe that there's what we call a halocline, which is an area of the water column where there's a rapid change in salinity. So I'll write that on the board. I don't think I have it on the slide. It's an analogous to the thermocline, but the halocline, halo for salt and cline for this kind of steep line, is the depth range. salinity change.
Can you explain the second to last one? So like as the
Oh, yeah.
ocean's eroding more like salt and everything, so the evaporation from the rains kind of balancing it?
Yeah, so what's amazing about chemical oceanography is that on a huge geographic scale, the ocean is in balance in terms of all the major ions for salinity, in terms of what's coming in from erosion from the land, and what's being deposited and removed from the oceans in deposition across the ocean floor. And so you can go anywhere in the world's oceans, and even though the salinity might change, 31 over here, 36 over there, the proportion of ions is the same in each of those bodies of water. There's always going to be a ratio of 3 magnesium ions to 4 sulfate ions, let's say. Even though the total changes, the ratio stays the same because the processes that are adding ions to the ocean are equal to the removal processes. It's pretty cool.
What would happen if we just got like 100,000 tons of salt that dumped in the ocean? Would it regulate again?
It would, but it would take a long time.
Okay.
It wouldn't, we could do it in a day. Not really, but you could do it in a day, but it might take a million years for it to even out. And again, it might come into balance at a different salinity than 35. What's interesting about that kind of equal proportion of these different ions is that before we discovered hydrothermal vents in the 1960s, late 1950s, chemical oceanographers postulated that there must be another removal and addition process for some of these ions in the world's oceans. And we just didn't know where that was yet. When we got down deep and we found these hydrothermal vents that were both dissolving ions at a certain rate with this hot water and then having deposition of other ions, it balanced it. And they were like, oh. It was one of those like, yeah, we get to write a big paper and do things. We're going to measure salinity in class. Again, it would be nice if we were doing it this week, but we're going to do soils. We'll measure salinity of soils too. All right. The next variable that we see in water is oxygen concentration. And we measure this as dissolved oxygen or DO concentration. And again, we talked a little bit at the start of class on Tuesday about the dead zone in the Gulf of Mexico and how it was a region of low dissolved oxygen concentration for organisms caused by excess phytoplankton blooms and microbial decomposition that used up all the oxygen in the water. The amount of oxygen in the water is limiting for organisms. It's not like being in the atmosphere where you're surrounded by oxygen. You have to wait, essentially, for oxygen to diffuse from the atmosphere into the water and then move to you, okay? And so many organisms have processes where they make currents of water that are constantly bringing them well-oxygenated water, okay? Fish are constantly opening and closing their mouths or swimming because they need to aerate their gills to keep oxygen and water moving over their gills. Some of them do it for food too, but everybody does it in order to get oxygen. Okay. They can't just stand there and breathe. They've got to move the water to get oxygen. So the gases diffuse from the atmosphere into the surface waters, and then it takes even longer for that oxygen to get down deep. This is a cycle though, and it moves on concentration gradient dynamics. Now you have a bunch of oxygen in the atmosphere. As organisms use oxygen in the water, they create a gradient of lower oxygen concentration to keep oxygen diffusing in from the atmosphere.
Isn't most of the oxygen come from plankton?
Yeah. Oh, yeah.
Okay.
And so in places where you have a photosynthesizer that's making oxygen, you'll have localized higher oxygen concentrations next to that organism because they're pumping out oxygen. It takes time to diffuse. Like on the local dynamics, you'll see it like bacteria will congregate around these organisms because there is more oxygen. But on the big time scale and big organisms, it's well mixed for most purposes. There's less of a gradient that they would be like. You don't see fish like cozying up to kelp because there's more oxygen. That's not the main driver why they're there. Okay.
Gotcha.
But that is true. All right. The solubility of oxygen depends on its solubility in both the air as well as in the water. It's So get, again, this kind of gradient of oxygen that's present. For this class, again, the big understanding is to recognize that oxygen that can be in the water varies on two things. It varies with pressure, and the amount of oxygen that can be in the water varies with temperature. So the amount of oxygen that can be dissolved in the water, the solubility, increases with increasing pressure. The higher the pressure, the more oxygen you can put in solution. So this means that you go down deep in the ocean, you can have more dissolved oxygen in the water than you can at the surface.
So are the depths more oxygenated than the surface water?
In general, but there are always exceptions.
Gotcha.
Again, it's like a general rule, and then the fun stuff is one that's not true. Again, we love in teaching to set up these two things, right? The deeper you are, the colder it is, the more oxygen you can have. But it is always a gradient. Okay, so more oxygen at depth. The other thing is that oxygen solubility decreases with increasing temperature. So cold water can hold the most oxygen. As the water warms, it can hold less oxygen. And this is true of carbon dioxide too. When you have something under pressure, you can shove in a lot of carbon dioxide. You can carbonate a beverage, but as soon as you release that pressure on the can or you open the bottle, all the carbon dioxide bubbles out of solution. The other thing too you may notice, and one reason we serve our carbonated beverages cold is that this prolongs the time that the carbon dioxide is dissolved in the water. And so it will stay bubbly and carbonated longer if it's on ice or served cold than if you take your Coke and you leave it in your car all day like I tend to do, it's flat because all the carbon dioxide is gone from the warm liquid that's left. Okay, most organisms need at least 5 milligrams per liter of dissolved oxygen. They have a lower tolerance for oxygen concentrations. There are some organisms which are adapted for low oxygen concentrations, and they tend to be specialist bacteria and archaea that live in these oxygen minimum zones throughout the world's oceans. But by and large, again, big organisms, that macroscopic organisms need a minimum amount of DO, or you won't find them there. And that's where the dead zone comes into play. Once oxygen gets really low, mobile organisms leave, all the fish leave. Sessile organisms that are stuck there in low oxygen conditions die. And that again can really affect ecosystems. Mixing and water movement enhance water diffusion. So streams, shorelines, big storms will increase the contact of water with the atmosphere, and you'll get more dissolved oxygen in the water. So the quickly flowing stream, with all the little burbles and bubbles and rapids, has more oxygen in it than the calm pool.
Does El Nino or La Nina affect the amount of oxygen in certain areas? Or
it certainly does. So that cold, nutrient-rich water that's
upwelling
upwelled is going to be more oxygenated than the hot water that stagnates there next to the coast. The nutrient deficiency is a bigger driver than the oxygen, but the oxygen, if given long enough, will start to be a player too. Okay. Okay. We can measure oxygen as we're going through a water column, just like we can measure temperature. And that's what these graphs are showing you. For different temperature regimes, summer, fall, spring, and winter, we can look at oxygen solubility as we're getting deeper in the water column too. And we see some interesting things. And we can, what I'd say is we're going to start with the wintertime one this time with the ice scenario. It's kind of interesting when you have this ice, you have this really, really cold water at the surface, which promotes oxygen solubility. And so you can get really, really well oxygenated cold water at the surface right underneath the ice in winter. Kind of like winter migrate as I talk to you and gesticulate. But so it's kind of cool. Usually we tend to think of the surface waters as less oxygenated. In wintertime, when you have really cold water at the surface under ice, you'll actually have lots of oxygen. And then it will actually drop off with depth. Okay, as you get deeper down, in general, you're further away from the surface, you tend to get less oxygen from this diffusion type of scenario. Okay, the other thing that sets up very often in summertime and in a little bit less so in the springtime is we see stratification again in oxygen levels within our water column. Okay, here at the surface where the water is in contact with the atmosphere, you have lots of oxygen. As you get down into that cold water, even though you could have lots of oxygen here, because it's just dependent on diffusion from oxygen above, you actually have organisms doing a ton of respiration down here, and they use up the oxygen. Okay? Because you don't have good mixing surface to bottom because of that temperature stratification, you get a decline in oxygen at the bottom too. Okay? You have organisms stuck down here, respiring, decomposing, and they suck up all the oxygen. There's nothing injecting oxygen back in. That density temperature gradient affects oxygen. In the red line here then is the well-mixed fall water column, and you see nice oxygen top to bottom because everything is mixing with each other because we've broken down the temperature density stratification. Cool. As you can imagine then, as the oxygen, you can think of like one spot at the bottom of a, let's say, estuary. As it gets and loses oxygen in the summertime, if that's what's happening there, you might have certain species that go away because it's not enough oxygen, and then they'll come back in wintertime, fall, because there is enough oxygen.
Are these graphs more of like a lake, or is this for the ocean as well?
I definitely think of this as a graph of a deep lake, like one of our Great
Yes, I
Lakes,
thought so.
or an
Currents
ocean.
or something. Or an ocean.
Yeah.
Okay.
I wouldn't expect, other than in summertime, I wouldn't expect such a profile to really be changing for a shallow water lake, like something that's less than 50 feet deep, because there's enough radiation penetration for it to get top to bottom, and it'll be very similar top to bottom the more shallow you are. So yeah, there's kind of like a minimum depth to get this stuff happening, but sometimes it might surprise you, and it can be dependent upon other factors like water movement and turbidity. Like if you have a bunch of sediments in the water or a bunch of plants, you can get different profiles. Cool. Okay. So seasonal stratification can affect us. The amount of microbial decomposition can affect us. Those microbial decomposers are sucking in oxygen to do metabolism, and they can really affect DO concentrations. Where we see this in the world's oceans is where we see this OMZ, or oxygen minimum zone trend. And oxygen minimum zones are common in well-stratified water columns. You tend to see that at the surface, there's lots of oxygen because we have diffusion from the atmosphere. As you hit that thermocline region, you actually get all these dead algae and phytoplankton that get caught at that gradient of density, and they actually sit physically in the water column between the surface water and the bottom. And right there in the middle of the water column, then you have all this decomposition that's happening of all this dead stuff. And it sucks down the oxygen, and you get this big dip in oxygen right there where the thermocline is. And then oxygen goes back up as you get down low because you've used up all the organic matter, it's cold, and there's not much, there's lots of oxygen that's built up down. That's normal. This like high oxygen, low oxygen microbial decomposition in the thermocline, high oxygen in the deep water, in the open ocean kind of summertime scenario. We're starting to see that this persists throughout the different seasons in growing areas of the world's oceans. And this oxygen minimum zone is great if you're an organism that can withstand those conditions. But for most ocean organisms, that's not their preferred environment. And so as this low D portion of the ocean expands in the middle of the ocean, essentially, in terms of depth as well as geography, we're starting to see a shift in the food chain in these regions from the normal phytoplankton, zooplankton fish into just microorganisms. And that's different. That's different for fish productivity for us from our perspective. Okay. There's lots of really cool microbial work in OMZs. If you get interested in that aspect of ecology, or if you decide that you're really into microbiology, this is one place again where you can go from What are, the specific little protein chains that let an organism have this type of metabolism and eat this type of organic matter and poop out this particular type of compound? That's the pure part of this. The applied stuff is, what does that mean for ocean food webs when you get more of those things? Okay, does it mean anything? Cool. All right, clicking on through it. The next topic I want to talk about is pH, of course, and pH is another one of these defining environmental variables for organisms. Most organisms, again, have a fairly narrow range of pH in which they're comfortable. And most organisms prefer a relatively neutral environment, around 6 to 9 on the pH scale. I had a whole bunch of stuff about pH in the class before, you guys, because we're talking about ocean acidification. Remember that pH is a measure of the hydrogen ion concentration that's in a solution. And pH scale goes from 0 to 14. What part of the pH scale is an acid?
0.
Yeah, 0 to like 6 is an acid. What is a base on the pH scale?
Or 7 up to 14.
Yeah, like 8 to 14. That like 6 to 9, around 7 range is neutral. And so your tap water, normal water, fresh water has a pH somewhere in the 6 to 7 range. Seawater has a pH of about 8.1. It's slightly basic, but not so basic that like organisms have to do a whole bunch of crazy stuff about hydrogen ions. But it is a little bit basic. The pH of a solution can determine what organisms can live there, how they deal with this hydrogen ion scenario. And this is what we talk about the pH scale is like 0 to 14, and we're like, okay, you go from 7 to 14 is like a twofold change. It's a logarithmic scale. So for every whole unit that you change on the pH scale, the concentration of hydrogen ion changes tenfold. So going from 6 to 9, it's not like, oh, we went up 2 units. It's like we went up 100%. Okay. Or actually 6 to 9 would be 1,000. 6 to 8 would be 100. Okay. So small changes on the pH scale are actually big changes in hydrogen ion concentration. And that means that we can start to affect a bunch of chemistry. So it's very important that pH, whether or not we're going to be able to deposit calcium carbonate or if calcium carbonate dissolves. So what I have shown here in the picture are these little pteropod snail shells, these little planktonic snails that live all over the world's oceans. And when the pH changes from 8.1 to about 7.9, they shift their ability to deposit calcium carbonate into their shells versus have their shells dissolve. And so if you leave these little pteropod shells in about 7.9 pH seawater for 45 days, they go from this to that. And so just a little change in pH can be life-changing for an organism that uses calcium carbonate in order to build shells or bone structures. Definitely what happens in these organisms is that as pH changes in the world's oceans, it's not like their shell just dissolves. They spend more energy maintaining their shell. And so that means that they grow smaller and they make less babies because they're spending more energy on their own growth and maintenance rather than on reproduction success and population dynamics. Okay, pH definitely affects protein structure and function. You hopefully remember vaguely from biology that if you change the pH that a protein is in, sometimes it denatures and it gets all floppy and it doesn't do what it was supposed to do. That's definitely true for organisms. As they moved out of their preferred pH range, they can have lots of metabolic problems. And it plays a role in soil chemistry and freshwater chemistry. When we get to really low pHs, we tend to leach different ions out of the soil. And we move ions around differently than what organisms are accustomed to. And in some cases, that means that they lose access to trace elements that they have to grow. And in some cases, it makes ion concentrations so toxic that they actually can't live in that environment any longer when you change the pH. And this is true of aluminum in freshwater ecosystems. At low pHs, aluminum starts to leach out of the soil and accumulate in fresh water. And when that happens, it affects the soil chemistry to when the plants don't grow as well around that particular region. And so you get lots of erosion, which can affect the freshwater and the terrestrial ecosystem. But lots of aluminum in fresh water tends to make fish make a bunch of mucus. some reason related to their particular biochemistry. And when fish make a lot of mucus, they can choke themselves to death. And so this is one reason why acid rain is bad, not only for terrestrial ecosystems, but acid rain, which has a very low pH, leaches aluminum out of the soil and deposits it in fresh water, and then you get sterilized flakes too. Okay. And so again, we tend to think of pH like, oh, the pH is this, but small changes can have big effects on organisms, and it's easy to unbalance the system sometimes. In seawater, we have this carbonate system that tends to balance and buffer pH. That's not available in freshwater ecosystems, which is why they're really susceptible to these types of pH changes on a short-term time scale. Cool. I don't know why my examples are always negative. I'm like, and then everything dies. That's just how it goes. Okay. All right, so I mentioned that changing pH in ocean water is linked to ocean acidification, which is what this equation is showing you. So one of the questions at the end of chapter 3 in our textbook says, what is the effect? Oh, I can make it worse, that's right. What is the effect of increasing carbon dioxide concentration on pH? And so carbon dioxide concentration is linked to pH in this equation.
Yeah.
Now it's going to be off at the top. So if you increase carbon dioxide concentration in the world's ocean, what happens to pH?
It's less acidic. Basic.
Nope,
It's more acidic.
more acidic. Okay, you got it. All right. If we increase carbon dioxide concentration, we push these chemical reactions to this side,
Oh, there's more hydrogen.
and you get more hydrogen ion concentration, which is an acidic solution. I didn't talk about the exact relationship between pH and hydrogen ion concentration, but it's a weird one. Like you know it, but then you ask a question like this and you're like, oh my God, I have to use that information. Remember, low pH numbers are actually high hydrogen ion concentrations. Like I always say. And this is a problem with ocean acidification. When we get lots of carbon dioxide in the atmosphere, the carbon dioxide dissolves through the water. And it goes through this chemistry, and it makes a lot of hydrogen ion concentration, which drops the pH of the world's oceans.
So more plants in the ocean, or more basic it gets, more organisms, more acidic it gets.
Yeah, to some degree. And again, like local conditions will affect the local pH just for that change in carbon dioxide concentration sucking in or putting out. Yeah, definitely. In the realm of ocean acidification, the ocean's pH has changed about 1/10 of a pH unit due to ocean acidification
How long?
in about 50 years. And so we went from 8.2 to 8.1.
Is that a lot?
It's a 30% change in hydrogen ion concentration. But a 1/10 of a unit of pH, but it's 30% more hydrogen ions.
That is actually bad.
It is bad. That's what causes the problems for organisms in building their shells. It has a problem. It's a big problem for coral reefs that want to deposit calcium carbonate. Then they have to compete with the hydrogen ions for carbonate ions. They spend more energy trying to grow and less energy actually growing and reproducing. And that affects populations. And it's not just corals, it's snails, like I talked about, these little sea snails. It's mussels, it's clams, it's oysters. We know low pH can affect the development of some larval forms of things like crabs. It actually makes lobsters grow bigger, just kind of cool. And it's actually really good for seagrass beds at the same time that it's bad for coral reefs. It's twin slow carbon dioxide. So we talk about ocean acidification as like the other CO2 problem. And it's caused by this type of basic chemistry and changes in pH. And it affects just some types of organisms. But when it affects something like coral reefs or an oyster reef or a mussel bed, then you're changing the foundation of the ecosystem. You're shifting from a coral reef to a seagrass bed. And that's going to give you different organisms, and they're going to do different ecosystem functions.
So what's increasing the amount of carbon dioxide? Just the amount of humans on the planet, or the technology we use, or?
The technology we use. So our burning of fossil fuels is what.
We'll go from the atmosphere and go to the ocean.
Yes, exactly. exactly. The more is in the atmosphere, the more will be in the ocean, the more hydrogen ion we'll have. Without the world's oceans, our climate change problem would be more severe because they suck up about 60% of our CO2 emissions, but not without consequences. Okay, one of the last things I want to mention to you guys today is that water movement, of course, can affect lots of these different variables that we've talked about in a particular place. And in water movement, we're going to talk about velocity, and we measure flow rates. And when we go out to these different places at Cincinnati Nature Center for the day we do aquatic sampling, we'll have a little flow meter. We'll see. Hopefully we go to a stream and not just 3 different lakes where it's like. But we talk about it in meters per second. The steepness of the topography, the volume of water that's going through a given area will affect the flow rate. The steeper it is, the more water pushing through an area, the faster the flow rate. The faster the flow rate, like in the top picture, the more oxygen diffusion you'll have, which we talked about. It tends to be cooler, but you'll also get more erosion. You'll get more bottom scoring. You'll get bigger rocks and pebbles and moved downstream. And you'll get different than deposition of sediment particles at the bottom. Okay. Quieter waters, lower velocity, you tend to get substrate accumulation rather than erosion. The stuff that was being carried by the water now has a chance to fall out of solution and settle on the bottom. You get sandy, mucky, clayey bottoms of rivers and streams versus pebbly rock stream bottoms when the water's flowing really fast. And the areas where the water sits for a little while or moves very slowly, you tend to have time for the process of decomposition to take place. So you may get more nutrients, but you may also get lower oxygen because the decomposers are taking it. So how would water movement affect nutrients?
Like you're gonna have smaller, like mossier plants up where water's moving faster, and then down where water's moving slower, you're gonna have like longer, grassier, more lush plants.
You're right. So water velocity affects what type of autotrophs you can have in the system. If they can't hold on, they can't grow. And generally, they can hold on and dig in, and you get these bigger, kind of lush, longer-lived plants than the plankton, little licheny moss-like stuff when the water's moving really fast. Okay. How would that affect nutrients?
Will there be more nutrients in lower velocity? Or opposite?
I would say the opposite.
I keep doing this.
I was like, you're having an opposite day. If you're having that on the test, just pick the opposite of what you think the answer is. No, I'm kidding. Don't worry about it. Yeah, higher velocity tends to be more nutrients. You have more erosion to pull stuff in. And you don't have autotrophs and organisms taking in a lot of nutrients because they're all tiny and they're fast-lived. When you get to the slower waters where it stagnates, then you have the chance for nutrients to be taken up and removed from the water or deposited on the bottom. You also, though, have the chance for regeneration with decomposition. And so they can balance each other, too. And it will depend on the particular environment. Definitely in terms of suspended particles, less suspended particles in fast-moving water, everything's being blown away, lots of dilution. Here you can get the buildup of particles in the water column. You get these darkish, tannish waters that are filled with sediment as it's depositing out from these kinds of
So why do you say there's more nutrients in higher velocity? Because the organisms don't have time to get it?
Yeah.
Okay.
The other factor there is erosion, and that as you are eroding away the shoreline and the rocks, you're weathering in nutrients to pump into the system. Okay, let's see. Definitely when the more wind you have, the bigger the waves you're going to have. There's a direct relationship between the higher the wind velocity, the bigger the waves you get. The longer the wind blows, the bigger the waves you get. We're seeing that with Hurricane Dorian right now. Long sustained winds, big storm surge and waves pushed into the shoreline. When that breaks down, then you get, again, stratification of your water column. Waves can mix water columns. They can move warm water down deep just with the circular action of the water particles in order to mix temperature, nutrients, dissolved oxygen down. For shorelines, which is one place where we see lots of different ecosystem variations along different types of shorelines, lots of wave action, like in the picture, leads to rocky shorelines. You're constantly eroding away the shoreline. Different organisms live in high wave action rocky ecosystems than on sandy, less wave action shorelines. Okay, less wave action, the water runs up, it runs down, it moves the sand particles, but they stay in place in general. You don't have these sweeping and scoring away of big wave action. And again, you'll get totally different types of environments and autotrophs and heterotrophs, rocky versus sandy shorelines. And that's largely determined by wave action, whether it's rocky or sandy. A little bit is substrate. Does that make sense? Yeah. What's really cool is in, like with Dorian, as we're seeing now, as it's moved across the Bahamian Islands, it has eroded away the island and it's depositing that sand, that sediment offshore. And so it's like moving the island in the direction that the hurricane is going. Taking sediment from the island and it's dropping it back behind the island in the path of the hurricane as it moves past it. And so you get this slow migration of islands due to both wave action and this type of storm action like Dorian.
I guess it's better than just like taking it like they like see ya. Like
Yeah, oh yeah.
it's a good thing that it's
No,
like
it
migrating.
drops it.
Yeah.
Again, it's just not where it used to be, where you had your house. Okay, all right. The last thing to remind you guys of course, is that the substrate, the bottom material, as I mentioned when we talked about salinity, matters to the type of ecosystem you're going to get in an aquatic environment. The types of soil particles and texture that you have, the types of ions that are available as nutrients from that type of rock that's actually there underneath the water will affect what types of organisms grow there. And so we're going to play a lot tomorrow with particle size and texture, as well as organic content. And that is going to be directly related to what plants grow on land, which is where we're going here. But it also affects what organisms grow and live in the water too, because it's still the same substrate. What substrate is there is dependent upon geology and geography, as well as water movement. And again, you're going to get different organisms that live in between clay particles, which are really tiny, than in between sand particles, which are much bigger. You're going to get different types of plants that can grow on bare rock versus sandy substrates. And again, just as on land, autotrophs build the food web and the type of community that we're going to find in the aquatic ecosystem. And so what plants grow where, temperature, salinity, dissolved oxygen, substrate, water velocity, affect what fish, shrimp, mollusks, sea turtles we're going to find in that location, or not at all. Okay. Okay, is there anything else? Oh, okay. Let's check. Oh, all right. Few last things. Again, I mentioned this substrate affects nutrient availability. If it's not there to be dissolved or eroded in the rock, it will not be available for the organisms. And so the substrate that's there that the water is dissolving affects nutrient concentrations. Runoff from land also affects nutrient concentrations. If you have lots of precipitation, you're going to have lots of nutrient input to a body of water. If you have lots of wave action to erode the shoreline, you have potentially lots of input into the shoreline. This means that how close you are to the land affects your nutrient concentration and availability. Near the land, lots of nutrients coming off the land. Out in the open ocean, nothing. Okay, you gotta rely on desert sand being dropped on you. Okay. Depth also plays a role. Shallow, lots of nutrients. Down deep, lots of times less nutrients. But it depends on your relationship to decomposition too, and what's actually happening in your area. Okay, the last thing is turbidity, which is our measure of suspended particles in solution. Here we see the inflow of a river into a larger lake ecosystem, and we can see the influx of suspended particles in that river as it's entering the clearer water lake ecosystem. And the amount of suspended particles is what we call turbidity, and we'll measure it in a couple of different ways, but essentially the higher the turbidity, the cloudier the water is, the more suspended particles. So higher turbidity means more suspended particles. And that tends to affect primary production. The more stuff is in the water, the less light gets to autotrophs. So the more stuff, the cloudier the water, the less primary productivity you will have. And that then will affect what food web you have higher up. Okay. Low turbidity water, clear water, like in the depths of the lake, lots of light coming in, all the wavelengths of light are available, tends to be more supportive of primary production. It all comes back to the sun. Okay, that's my spit for today. We are done with chapter 3. Tuesday we'll be in chapter 4. Tomorrow is definitely based on chapter 4 in our textbook where we're talking about terrestrial ecosystems and soil. Homework is due today. If you have it, I'll take it. If you're turning it in online, do so by midnight. Okay? Thanks, guys. Take more bananas with you. Oh my God.